Hello. Let's take an example, basically to show how some systems can be modeled using the continuous time Markov chain. So we have a small factory with 3 machines and 1 technician to repair the machines. The machine is in the working state for a time that is basically exponential mu. Okay, so the average is 1 over mu units of time. The technician can work on 1 machine at a time, and basically the surface time, so basically the time needed by the technician to fix a machine is exponential of alpha, because the average time is 1 over alpha. And then x of t will be the number of working machines at time t. Okay, so this will be, so the state will be the number of working machines. So this will be x of t belongs to, so it may be the case that all machines are working. So we have 3, or 1 of them is not working, or 2, or basically the 3 of them need fixing. Okay, so this is the state space. The first part of the problem requires the infinitesimal generator Q, or the transition rate matrix. Okay, so so how can we think about this? And again, like, things here are, there is no trick. And when I give you problems like to model using CTMC, there is no trick like you start doing or you discover that actually the system cannot be modeled as a CTMC. If, it will be taken for granted that you can model the system using CTMC, and the questions are something like this. So what is the transition rate matrix? What is a stationary distribution, and so forth? Okay. And as you can see, everything is prepared to have a CTMC, and everything is like, exponential, which is a key ingredient. If you see something other than the exponential distribution, then definitely we are not in the domain of continuous time Markov chains. Okay, so now let's construct our CTM. So now it's the Q matrix. It's the transition rate matrix, so 0, 1, 2, 3, 0, 1, 2, 3. Okay. And now we can do the last row first. Suppose that the 3 machines are working. Suppose that the 3 machines are working. So what is the transition rate to go from 3 to 2? Which means that, if you go from 3 to 2, this means that now 1 machine basically broke down. And so what should be written here? So this is the rate of going from 3 to 2. And then, of course, like, we know the properties of the Q matrix, and these are very useful in constructing those in problems like this. The sum of the elements in the row, the sum is equal to 0. Okay, and then on the main diagonal, we have non-positive elements, and the off-diagonal elements are non-negative. So what is this guy? To go from 3 to 2, which means that 1 machine breaks down. So in state 3, there are 3 machines working. Okay, so let basically be, T1, T2, T3. So Ti, let's say it's the time to break down for machine I. So basically, to go from, what is the distribution governing the transition from 3 to 2? It is the minimum of those guys, T1, T2, T3. So the 3 machines are working, okay, and let's say the residual life of each of them is exponential with the parameter mu, and then one of them, which is the guy with the minimum residual time, will break down, making the state of the system 2 rather than 3. And again, here we don't have like control over the definition of the state. The problem itself tells that the state is the number of working machines. Okay, so and in continuous time Markov chains, you typically see this, that you have something that is the minimum of independent exponential distributions. And the fact that we still have a continuous time Markov chain is this result. It's a widely used result, which you can show easily, that the minimum of independent exponential distributions, so the minimum of, so if you have random variables, x1 plus x2 plus x3 and so on, and this is exponential lambda 1, this is exponential lambda 2 and so on. Now the minimum of those guys is, so x1, x2 is exponential, okay? Because again, like if you deviate from the exponential distribution, then actually there is no meaning to use the CTMC. So this is exponential, and you sum the parameters. Those are called the rates of the reciprocals of the means. You just sum them. Okay. So here what we have is the minimum. So to go from 3 to 2, one machine will break. Okay. Which one of them? Well, it's the one with the minimum residual time. So it is a machine. It has been working for a while, and then there is a remaining time to break down. And the nice thing about having exponential times, for the time during which the machine is working properly, is that the remaining time also has the same distribution. So because of the memoryless property of the exponential distribution, it's not like a renewal process in which like the residual distribution can be something very complicated. Here, simply if you talk about the time, it's the same as talking about the residual time or the remaining time. Okay, so if you have 3 exponential random variables, basically the rate will be exponential mu plus mu plus mu, so it will be exponential 3 mu. So here we have 3 mu. Okay, so this is very important. This 3 is very important, again, because you go from 3 to 2, and any one of those machines can break down. Or the best way to understand it is to think, again, because this is like sort of fundamental or inherent in continuous time Markov chains, this idea that you have the minimum of exponential random variables. Okay, and so here again the distribution of the minimum. So this is distributed as exponential 3 mu. And basically for this event to happen, okay, so if this minimum, we can basically say it this way, that 3 remains in 3 if this exponential 3 mu is greater than delta t. So if you study, as we did at the beginning of continuous time Markov chains, if we focus about an infinitesimal time duration and ask what is the probability that exponential 3 mu will remain basically, or its value is greater than basically delta t. So this will be the probability is 1, right? So this probability is, it is exponential minus 3 mu delta t, which is approximately 1 minus 3 mu delta t. Okay, so this is the time in which you stay in the system. In the state 3, okay, and this parameter minus 3 mu is what you should write here. Okay, you do not need like to remind yourself of how these things were derived. In fact, it's you can just I think like in the solution that I wrote down, I just wrote it directly. Again, like once you capture the idea, even this business of having minimum and so on, you will like have it just in front of you once you read the problem. Okay, so you don't need like to justify or like write a big story about why it should be this one is 3 mu or this one is minus 3 mu. And then you have zeros. Okay, and remember that basically in continuous time Markov chains, the probability that to have like in infinitesimal time to have more than one. So in infinitesimal time, it's either that you remain in the same state or you do one transition. You just do one transition. The probability of having more than one transition is negligible relative to having one transition. Now, note that if you want to go to 3 to 1 from state 3 to state 1, this means that the lifetimes of two working machines basically are exactly the same. So it means that like two of those guys are exactly the same. Exponential random variables are continuous random variables, and the probability that two of them are exactly equal, this probability for independent, if T1 and T2 are independent, probability that T1 is equal to T2 is exactly equal to 0. Okay, so there is really no need to worry about like going from 3 to 1 or 3 to 0. Again, like to have such an event, it means that two independent continuous random variables are equal, and this happens with probability 0. Okay, now if the system is in state 2, which means that there are two working machines. Now, if there are two working machines, then how do you go from 2 to 3? 2 to 3. So 2 to 3, it means that there was a broken machine, and then the technician worked basically to fix the machine. To go from 2 to 3, we need now to use the distribution, basically describing the amount of time needed by the technician to fix one machine. Okay, and so if you have one machine that is out of surface, now it can be brought back to surface, and this will happen with a rate that is alpha. And to go from 2 to 1, it means that, so there are two working machines. To go from 2 to 1, it means that basically one of your two machines will break down. Okay, so this will be with a rate 2 mu. 2 mu again, because if you start in a state, I need to align the rows here. Okay, so this is 3, this is state 2, and then 1 and 0. So to go from state 2 to state 1, again, you have two working machines. One of them is already being repaired or something, and one of the working two will break down. So specifically, we have the minimum, under the hood. Basically, what is going on is that each one of those two working machines, it has a remaining time or residual lifetime, and and so basically the distribution of time needed like to go from 2 to 1 is the minimum of two of those exponential mu random. So those have the parameter 2 mu. And here 2, it means minus alpha plus 2 mu. And this is 0. You cannot just go from 2 to 0 directly, unless like two machines break down at the same time, and this event, it has a probability 0. Then if you are in state 1, from 1 to 2 means that one machine now is back in business, and so this will be alpha, this will be 0, and the technician works on one machine at a time, so he cannot like fix two machines at the same time, and so this will be 0. And now what about here? So you go from 1 to 0, so you have just one machine, and now it breaks down. So this will be mu, and then you can just take this element as mu plus r. So what I'm doing here, if you focus that, I am focusing on the off diagonal rates, and based on that, once you know these guys, use the property that the sum of each row is equal to 0 to get the guy that should be on the main diagonal. Okay, and finally 0. Zero means that actually 0 machines are working. So the 3 of them are sick, and basically what you can go from, or like the state that you can go to is a state 1, and this will happen like so. The technician will basically work on one of those 3 machines, and basically with the rate alpha, again it's the same, this parameter of the exponential distribution characterizing the working time of the technician. This will be alpha, and automatically this will be minus alpha, and here we have 0 and 0. Okay, so here is in a less cluttered form. Okay, so this is basically the transition diagram. Here I omitted, I typically omit the self transitions, and this is the Q matrix. Again, it's a matrix that describes basically the system, and yeah. If we have 2 technicians, it will be 2 alpha. That's true, because I mean, basically now to go from 0 to 1 and 2 technicians are working, then exactly, basically to go to 1, I mean, you need for one of them to, you need either to finish. Okay, so it's like a minimum, and then the minimum will have a parameter 2 of 2 surface times. Here it will be 2 alpha, and then it will be 2. Okay, so keep track of this. Those are sort of the annoying guys. I mean, sometimes people like forget about them, and they, of course, I mean, they are what you need to have a correct state transition, so to have basically the correct Q matrix or transition rate matrix. What else is needed here? The stationary distribution. Okay, so this is the Q matrix. Okay, and the stationary distribution, like you just try to solve the eigen equation. Pi q is equal to the all 0 row vector, and so you write down this thing. You put a vector pi 0, pi 1, pi 2, pi 3, and you start writing down your equation. So you have pi 0, pi 1, pi 2, pi 3. Now, if you take this row multiplied by the first column, you have minus alpha by 0 plus mu by 1. This should be equal to 0. And from here, you can establish a relation between pi 1 and pi 0. And then you take this guy and multiply by the second column. So this will give you an expression involving pi 0, pi 1, and pi 2. But we already know pi 1 in terms of pi 0, so this can be basically manipulated algebraically so that you have pi 2 in terms of pi 0, and then you have the final one, which is, this is pi 3. Then, so every guy now is in terms of pi 0. You can just say, well, we should have a sum of probabilities equal to 1, and by doing this, you have pi. So basically, each one of those guys has this pi 0, and pi 0 itself is given by this expression here, which depends, of course, on the parameters of the system. So alpha, which is the parameter of the exponential distribution related to the working time of the technician to fix a machine, and mu, which is the time basically till breakdown. So this is an example, and like in homework 13, you will find like sort of it's a bit more complicated case, but the main ideas are exactly the same. Okay, so let's go back to DTMC. So this was a digression. I said I will not even like be rigorous or very exact with CTMC. But of course, it is a trick that you need to have in your bag. I mean, this is undeniable. But we'll go back to DTMC, and we'll focus on a number of like famous problems or famous models that are very, very useful. Okay, so one of them is gambler ruin problem. Okay, which is actually, so this is the solution. This is the solution to homework 12 problem 8. Okay, so before actually telling you what is this, you know, this is the gambler ruin problem, which is basically n+1 states, and the very first one and the very last one, so state 0 and state n, are absorbing states, and then the states in the middle, basically you can there are no self transitions. So basically the probability of remaining in some state between 0 and n, the probability is 0. You need to make, at each time step, you need to make a transition with probability p to the from n, let's say from n-1 to n, and then with probability q, you go from n-1 to n-2. Okay, so this is basically the so-called gambler ruin model. And the reason it's called like this, it's you know, you can imagine that some guy is gambling, and he starts with a certain sum of money, let's say with $2 or something like this, and that, like, in each step the guy wins an extra dollar, basically with probability P, loses a dollar with probability Q, and then the game finishes if the guy loses all the money. Okay, so he will be in a state 0, or if the guy basically can collect up to n dollars. Okay, so if he reached that state, he can keep the n dollars and get out of the game. So I mean, of course, the model itself is abstract, and it can be used in numerous basically system, you know, to model numerous systems. But this is like the reason it's called a gambler ruin. It's the time. So basically, absorption in state 0 is the ruin event, you know, in which basically the guy will lose the money, and that's it. Okay, so in homework 12, problem 8, Rn and Un. So Rn is the probability of absorption at state 0 if the initial state is n. Okay, so this is the probability that it's the probability of ultimate ruin. It's the probability of losing the money. But of course, I mean, you know, this chain can be describe many other things. And I think till now, I haven't finished the grading, but till now I think everyone got this correctly. The problem is in this one, the average number of steps starting from n till absorption at either 0 or n. So again, it's different. So here, this one is the probability of absorption at state 0. So this is the probability that eventually you will be absorbed in state 0. And 1 minus Rn will give you the probability of being eventually absorbed in state n. Mu n is the number of steps basically from the beginning till absorption at either state, at either 0 or 1. Those are the expressions for Rn and Un. And Mun, basically, I think till now I have seen just one correct solution for it. So what should be the difference equation for Mun? Again, like in the solution, that, like the first part of the solution that I wrote down, like there is like this, you know, talk about the F probabilities and how actually to show the how the difference equation is written. But of course, once you get the idea, you start writing down these difference equations directly. So what is Mun? What is the average number of steps basically to be absorbed in 0 or big N, given that you start in small n? So for this one, again, like what are the possible transitions from state n? Again, take state n to be one of the intermediate states from 1. So here n is from 1 to big N. Well, you know, you can do B and go from n to n plus 1. Okay, so this should be, so mu n plus 1, right? So with probability B, you go to n plus 1, and with probability Q, you will have Qn minus 1. So far, so good. But this is wrong. Okay, and so again, like except one student, basically everyone like wrote down this thing, which of course is wrong, because now it's not, we are not talking about probability. We are counting the number of steps, and to go from n to n plus 1, that's a step. That's a step. And to go from state n to state n minus 1, that's a step. Okay, so you should have this plus 1 and this plus 1. And so this is P mu n plus 1 plus P plus Q mu n minus 1 plus Q. And this P plus Q is equal to 1. Okay, so if you do this, then basically you get these two results. One of them is for the case in which P is equal to Q is equal to 1/2, and this is basically the other case. Now I'm providing these results because, like, maybe later you find that you encounter a problem in which, like, it fits this model. It fits it. You find that, oh, I basically have the gambler ruin. You know, the problem may sound very different from gambler ruin, but the model is exactly the same. Like, you have two absorbing states, and then you basically do these no self transitions. You do transition, you know, one state, you know, from n to n plus 1 with P, from n to n minus 1 with Q, and so on. In that case, if you find that your problem matches the gambler ruin model, then you can use any of those results that you can see directly. Okay, the trick is to recognize that by the end of the day, you know, the problem that looks very different is actually gambler's ruin. Okay, so no need to, like, redrive any of those results. You have the results for the probabilities and for the time till absorption. They call it time till absorption. In either 0 or n, you know, you have everything here, and you can use them directly if needed. Okay, and this, you know, this applies to homework 13 or homework 14. Perhaps homework, you don't have this in homework 13. You will find something relevant in homework 14. Okay, so that's the gambler's ruin problem. And then you know, some other issues. Sometimes, you know, sometimes it is interesting to take limit n goes to infinity, which basically makes it like sort of one absorbing state. Okay, so sometimes, you know, we have take the limit as n goes to infinity, saying that, you know, basically it's like the number of states becomes infinite, and it is like one absorbing state. Okay, so so this is another thing in which, like, you can basically put n, take the limit if needed. Okay, so now let's go to random walks. So a random walk, it's a more general term. A random walk, you know, some people define it actually as the sum, so a running sum of IID random variables. You know, if you have a summation, you know, x1 plus x2 plus x, you know, something like this, or like d1, d2, d3, regardless of the distribution. So something running of ID, so basically this will be a sum of, so xn is equal to sum of k from 1 to n dn, and those guys are IID and can have any distribution. Okay, but here I will focus on the case in which dn is plus or minus 1. Plus 1 with probability p and minus 1 with probability q. Okay, so again, those are like the steps, okay, the steps that you can basically accumulate them, as I will do here, and have defined xn to be xn minus 1 plus dn, or that xn is some fixed value plus a summation. So again, this summation typically is applied to IID random variables, and here, when I say random walk, I mean that the step, which is dn, is a random variable that is plus 1 with probability p, minus 1 with probability q. But you can find, like, you know, some general you know, PMF or something like this. Okay, and here note that I am restricting how you do the transitions. Okay, so d1 dn is equal to plus 1 or minus 1. You know, when I make this basically a Markov chain, I will only allow transitions like in the gambler ruin, like you go from n to n plus 1 or n minus 1, as we'll see. But I mean, let's do it step by step. So we have an IID, two-valued process, dn, and so every d is independent of the others, and this is extremely important, as we'll see later. Dn is plus 1 with probability b, is minus 1 with probability q, which is 1 minus b. Now, what are the statistics of dn? The expectation is 1 times p plus minus 1 times q, and this will be b minus q. The second moment, you will have 1 squared times p plus minus 1 squared times q, so this will be p plus q, which is equal to 1. And the variance is the second moment minus the square of the first moment, so it is 1 minus p minus q squared, and then typically it is written as 4pq because you can take this one and write it as p plus q squared, and then you can expand this and this. P squared from here will eliminate p squared from there, q squared with q squared, and here from here you get 2pq, and from here minus, and from here minus 2pq, so you end up with 4pq. So the variance is 4pq. Okay, now our discrete time Markov chain will be basically x of n, in which you take a fixed number and then you start summing these from 1 to n. And typically this you can say initial state or starting point will be 0. So we'll typically start from 0. So without loss of generality, let's x0 is equal to 0, and so x of n is equal to the summation k from 1 to n dk. Again, don't forget those are IID, and they are basically plus or minus 1 with probabilities p and q respectively. And of course, x of n minus 1 is summation k from 1 to n minus 1 dk, and the difference between x of n and x of n minus 1 is basically dn, or x of n is equal to x of n minus 1 plus dn. So basically, that's the reason it's called the walk, that, you know, by summing, you are basically, you know, accumulating and till you reach x of n. So x of n is the previous x of n. So it's x of n is x of n minus 1. It is the the sum that you reach at n minus 1, and then you add to it the extra term d of n. This is what we will what will move you from basically x of n minus 1 to x of n. Okay, so so you can imagine that this this chain is, so you have 0, you have 1, you have 2, you have minus 1, you have minus 2, you have 3, and you have minus 3. And you start at 0, and then with probability b, you go here like this. With probability q, with probability q, you go from 0 to minus 1. So x of 1 is either 1 or minus 1 or 1, right? So you start at 0. Then so x of 1 is just equal to d1, and it is minus 1 or 1. But then what is x of 2? Well, x of 2 will depend on what first step you took. So basically, if you go to 1, then now you have 1, but perhaps d2 is equal to minus 1, and so this will bring you back to 0. You are at 1, and then you know, minus 1 will basically make a transition from 1 to 0. But you can also, with probability b, you have additional 1. Okay, so x2 is d1 plus d2, or is equal to x1 plus d2, and this can be actually equal to 2. And is there a possibility that you know, you will remain at 1? Of course, no, by definition, because, you know, you add those steps, and you know, once you are at 1, you need, you will add the extra d2, and d2 is 1 or minus 1 with probability 1. It's never 0, and so you will have to make a transition each time, and hence you can never remain at 1. You can be in 2. You can go back to 0, and basically from here you can go to 0, and you can q2 to minus 2. So here we have minus 2, 0, and 2. So the value of x2. So as you can see that x of 0 is 0. X of 1 is a random variable that can be minus 1 and 1. X of 2 can be a random variable that is minus 2, 0, and 2. And so note something. It emerges from here that at odd instance of time, x of n, so if n is odd, x of n is odd. At an odd instant of time, like x1, x3, x5, and so on, x of n must be an odd number. Why is this? X is a sum of d's, right? And the d's are plus or minus 1. So basically, each term in the summation is odd, because it's a number that is 1 or minus 1. And so what happens if you add an odd number of odd integers? By odd integers here I mean minus and plus 1. If you add an odd number of odd integers, it gives you an odd integer. Okay, and so basically this is very important to keep in mind that sum of an odd number of odd integers is odd. Okay, and this means that if n is odd, x of n must be odd. Now, if n is even, x of n is even, and the reason is that the sum of an even number of odd integers, and by the odd integers I mean here plus or minus 1, the sum of an even number of odd integers is even. Okay, so from the very beginning, you note that there will be instance, so any odd integer will be prohibited if the time instant n is even. Okay, and any at n, when n is odd, this is a time in which x of n must be odd. It cannot be even. Keep this in mind. Now we say that our random walk is simple if basically p and q is equal to 1/2. So this when p is equal to q, we say simple random walk. Or conversely, if I say we are studying a simple random walk, so automatically it means that p is equal to q is equal to 1/2. Now suppose that you have x of n, it is equal to this summation of n d's, and x of m, it is equal to this summation. Suppose that m is strictly greater than n. Suppose that m is strictly greater than n. Let's now study the difference between x of m and x of n. Well, the difference will be a sum of the d's from n plus 1 to m, right? So take this difference versus x of n, which is a summation from 1 to n dk. Okay, so now this is x of n depends on the d's from 1 to n. The difference x of m minus x of n for m greater than n depends on the d's at time indices n plus 1 to m. Recall that d is an IID random process, so the d's involved in xm minus xn are independent of the d's here, because this is from 1 to n, this is from n plus 1 to m. So x of n and x of m minus n are independent. Are independent. Very important. Okay. And so we say that our process has an independent increment. Okay, so again, so if m is greater than n, so you have x of n, you have x of m. Now x of n and x of m are not independent, but x of n and x of m minus x of n, those are independent. Now, what is the expectation of x of n? Recall that x of n is the sum, k from 1 to n dn. So this one will be n times the expectation of dn, which is p minus q. What is the variance of x of n? Now we are talking about terms here, and those terms are independent, and so the variance of a sum is sum of variances, and so this will be n times the variance of dn, which is 4pq. The second moment, is basically the variance plus the square of the first moment, which is this. Okay. Any questions? Now, let's study, basically this thing. What is expectation xm, xn? And this is a trick that is used in studying random processes in general. So you can find it applied like in random walks, Markov chains, Poisson processes, and so on. And now you want to find this expectation. Let's now make use of the result that the process has independent increments. So the trick is to take expectation xm multiplied by xn, and here you subtract xn and then you add xm. Okay, so you are doing nothing, but the idea now is xm minus xn, and xn, they are independent. And so this is expectation of a product will be product of expectations, expectation xn, and then you are left with expectation xn squared. So basically this this expectation here is the second moment, basically written on the previous page, and then you have this product here, expectation xn, this is np minus q, and the expectation of the difference basically is, expectation is linear, and so this one is easy. This will be m minus n p minus b minus q. Okay, so so this will be expectation xm xn. Now you can find the variance of xm minus xn. Sometimes this is needed, and sorry, the second moment of xm minus xn, and so you can just expand this, and for each one of those guys, there is again the expression is written on the previous slide, and then now you have expectation xm xn, which you can take it from here. Okay. The variance, xm minus xn is equal to the variance of this summation that goes from n plus 1 to m. Here I am assuming that m is greater than n, and those are independent. So variance of sum is sum of variances, and so basically you have here 4pq, which is the variance of dk, and then you need to multiply by the number of terms in this summation, which is m minus n minus 1 plus 1, so it's m minus n, like this. Okay, and then this thing here, note that this thing by definition, if we try to understand it in terms of random processes, this is basically the correlation function, right? So this is Rxx of Mn, it's the correlation function, and so basically the correlation function is basically this thing. So the correlation function is this. This is Rxx of Mn when m is greater than n. Okay, so basically when you write down a general formula for the correlation function, you should not assume that this is all. You should study every case. So one way of doing things is to reverse the role of m and n everywhere. So this is one strategy. The other strategy is basically to look here. What will happen if you have mn, right? So here is the product mn, and m is greater than n. Now if you switch the roles and you make n greater than m, this product will remain the same, right? But this other term, it has an n, and n is the smaller guy. So basically, if you make m less than n, you will get an m here. So if you see something like this, sometimes you can directly write down that the correlation function is p minus q squared mn. So Rxx mn generally is p minus q squared mn, okay, plus 4pq, the minimum of m and n. And as you can see that the correlation function depends on m and n. So the random walk is not a stationary process, because a stationary process will depend only, so the correlation function will depend only on the difference. You should see something like m minus n or n minus m or absolute value m minus n or something like this. But we don't have this here. We have a general function of m and n. So indeed, the random walk is a random process that is non-stationary. Okay, so this is the correlation function. Okay, and then you can, basically, if you subtract the means, you get the covariance function. And as you can see, it is 4pq, the minimum of m and n. The process definitely is not stationary. and you can compute things like variance of the difference. And now, if in the general case, if m and n, so when m is greater than n, we got m minus n here. If n is greater than m, this will be reversed, and generally the variance of xm minus xn will be the, you will have to take the absolute value here. Okay, again, these things you can do it again, like take the case of n greater than n, and then n less than, and then n greater than or equal to m, something like this. Or you can do one of the cases and try to basically generalize it directly. Again, it depends on your taste, and for similar problems, you do not really need to show every single detail. Okay. But now to the interesting stuff. So basically, in a first course on random processes, this is what you typically do. You have a random process. X of n is a random process. It is indexed by n, which is a non-negative integer. Basically, the possible values of x of n are integers. Okay, and we actually have the Markov property because given x of n minus 1, given x of n minus 1, x of n is independent of anything that has happened in the past. But let's now try to, again, if you recognize this as a discrete time Markov chain, then what about the B probabilities, the transition probabilities, and what about the first passage probabilities? Okay, so this will be the focus now, and the important part of this lecture. Okay. We want to compute this one. And we want to know basically whether this probability as a function of n, does it have a limit as n goes to infinity? What is the limit? Is it a positive number or 0? And if we sum this over n, will we get something that is finite or infinite? So again, this probability is not, something that is like useless. Once you get it, for example, you can classify the states of the random walk, again, which is a discrete time Markov chain. You can say that our states are, and then you can say transient or non-recurrent or positive recurrent. Now, note that the discrete time Markov chain of the random walk is irreducible, right? So so long as basically p is strictly between 0 and 1, any state is reachable from any other state. Any state is reachable from any other state. For example, starting at 0, is so basically is 100 reachable from 0? Is 100 reachable from 0? Well, yes. Basically in you can have, in 100 steps, you can basically have a sum 1 plus 1 plus 1. You have 100 ones. Okay, so P of x. So the probability that x of 100 is, the probability that x of x 100, so this at innocent is equal to 100, given that x of 0 is equal to 0. This probability again requires that you basically have 100 ones in a row. The probability of this event is very tiny, right? It means that you need to 1 and then a 1 and then a 1 and then 1, which can be a tiny number, but it is non-zero, and this is what is important. So remember the definition of accessibility, of reachability of a state from the other. Remember that I is reachable from J if there exists an M, and you just need one time instant such that Bij of n is strictly positive, and no one tells you that this probability should be like quote unquote significant. If Bij of n is like 10 to the minus trillion, it's okay. I mean, it's mathematically speaking, it is strictly positive, and so the states are reached from one another. So if you think about our Markov chain, so the sum is an integer, and you can reach any integer. Starting from any integer, and again, like the default is that we will start at the origin at so x of 0 is equal to 0. You can go to any integer. Every integer, for example, can be visited in a number of steps equal to itself, or equal to its absolute value. I mean, so you can go from 0 to minus 50 in 50 steps. You can go from 0 to minus 50 in 50 steps, like you have minus 1, minus 1, minus 1, minus 1, and so on. So you have a sum of 50 minus 1s. Now the probability of this event, yes, is q to the 50, but again, it will be a tiny number, but it is still positive. So actually our chain is irreducible, and every state is reachable from every other state. And this means the following. This means that if you can know basically that one of the states is transient, then everyone is transient. Okay, so so the random walk as a DTMC is irreducible. All states belong to the same class. All states belong to the same class. And here, in homework 12, number 5, it is interesting that basically most of the solutions I have seen so far are actually wrong. And, so people like, there are states that are clearly reachable from one another, and so like everyone got that state 0 is a positive recurrent state in problem 5, and from state 0 basically you can reach any state k if alpha k is positive. Alpha k is a probability that is defined in the problem, and we know basically this property that if a positive recurrent state leads to another state, in other words, if there is a state that is reachable or accessible from a positive recurrent state, or actually from a recurrent state, then the state itself is recurrent, and both the states communicate. So again, this is like sort of a fundamental result that you can basically, you need to keep in mind. You cannot have a state reachable from another state, and actually you cannot have a situation in which the states communicate, and then one of them is positive recurrent and the other is transient or something like this. Here in our case, every state is reachable from every other state, and so this long story I am saying is to justify the focus on P00 of n. It will tell you everything. Given that our Markov chain is irreducible, now if I reach the conclusion that state 0 is transient, then every state will be transient. Okay, let's first compute this probability that you go from 0 to k in n steps. You go from 0 to k in n steps. So what is the probability that x of n is equal to k, given that x of 0 is equal to 0? Okay, so x of n is equal to k is equal to summation j from 1 to n of dj. Okay, so x of n is equal to k if this summation here is equal to k. Note that if n is even, k must be even, and if n is odd, k must be odd. as I said when we talked about, this, again, this is a sum of odd integers because every d is plus or minus 1. So an odd number of odd integers will give you an odd result, and an even number of odd integers, when you sum them, you will get an even result. So n and k must have the same parity. N and k must have the same parity. What else? Now, suppose that, in this summation with n terms, that there are n1 terms or n1 steps, steps that are plus 1, and n2 steps that are minus 1. Okay, so we have here n terms, n1 of them are plus 1 and n2 of them are minus 1. Then n1 plus n2 is equal to n, okay, because each step is either plus 1 or minus 1. And then what will be this summation? We have n1 plus 1 and n2 minus 1, okay, and so basically the sum, so x of n, will be n1 multiplied by plus 1 plus n2 multiplied by minus 1, so it will be n1 minus n2. This means that if x of n is equal to k, n1 minus n2 is equal to k. Okay, so n1 plus n2 is n, n1 minus n2 is equal to k, and you can basically solve these two guys together and get that n1 is equal to n plus k over 2 and n2 is equal to n minus k over 2. Okay, so if I study the probability that x of n is equal to k, again, one way of thinking about it is to get the sum equal to k, to get xn equal to k, then we need n1 plus 1s and n2 minus 1s, and basically we should satisfy the following two equations. n1 plus n2 must be equal to n, and the difference n1 minus n2 must be exactly equal to k. And so given n and k, I can get n1 and n2 and vice versa, which means that specifying n and specifying k tells you exactly how many plus 1 do we have in the summation and how many minus 1. These expressions may look basically problematic because we have a 1/2 or we have division by 2, but they are not. Remember that we agreed that n and k, they have the same parity. So n plus k is always an even integer. If n is odd and k is odd, the sum and the difference is even. If n is even and k is even, the sum and difference is also even. And so dividing by 2, this n1 and n2 are guaranteed to be basically whole numbers. Okay. Now let's now write the probability. So the probability is this: for x of n to be equal to k, for x of n to be equal to k, among the n d's, there should be n1 plus 1. We should have n1 plus 1s. Okay, and n1 is n plus k over 2. We should have those. Now, and of course, the remaining ones, n2 will be minus 1s. Now, do we care about the order? Do we care about the order? No. I mean, so basically, among the n d's that basically are summed to give x of n, you need n plus k over 2 plus 1s. They can occur anywhere among the n d's. Okay, so that's the reason we have n choose n plus k over 2. So we have this guy saying that, well, the sum will not change if you take n1 plus 1s and basically play with them, put them in any in any term in the sum of n terms. So so it is n choose n plus k over 2, which tells you that basically so long as you have n plus k over 2 plus 1s and n minus k over 2 minus 1s, you are good. And now we have how many steps, how many times d is equal to plus 1? n1 times. Okay, and so basically you need to take p to the power n plus k over 2, or b to the power n1, and then q to the power n2. Okay, so again, like you have n1 plus 1s, n2 plus 2s. To have n1 plus 1s, we need n1 d's to be equal to plus 1, and they are independent of one another. And to be plus 1, this happens with probability p. So you have p to the power n1. And then you need to have n2 basically minus 1s. And so you have q. Now q to the power n2, and then we need also to account for the fact that basically the n1 plus 1s can be anywhere basically in the n terms, and so we multiply by n choose n1. Okay, and again, as I said above, that you can n1 plus n2 is equal to n, and n1 minus n2 is equal to k. So rather than writing things in terms of n1 and n2, you can write them in terms of n and k. And this indicator function, I think it is important. In some references, you will not see it written, but it is important actually to know what is going on regarding the relations between n and k. So, for example, something that we have talked about already, that k and n, they have the same parity. N is even, then k must be even. If n is odd, then k is odd. Otherwise, the probability is 0. The probability that x of 7 is equal to 18, that x of 7 is equal to 6 is 0. You cannot, x of 7 cannot be equal to 6. X of 7 cannot be any even integer whatsoever. And x12 cannot be any odd integer whatsoever. So basically, n and k, they have the same parity, which means that their sum or their difference is an even number. But there is something else, which is that the magnitude of k is less than or equal to n. And the reason for this is that this summation here, the summation j equals 1 to n dj, is upper bounded by n and is lower bounded by minus n. It cannot go above n, because the maximum that you can get is that all your terms are plus 1s, and in that case you will get an n, or all your terms are minus 1s, and then you get a minus n. Other things cannot happen. Okay, so it must be the case that k, magnitude k, is less than or equal to n. So this is the probability to basically go to state k. Now basically put k equals 0. So we are studying b0, 0 of n. So go to this expression here, put k equals 0. Then we have this probability n, choose n over 2, b to the power n over 2, q n over 2. Note that n is even. Note that here that basically n is even. You cannot be in state 0. Okay, so b0, 0 of n is strictly positive only when n is even. Okay, so we'll put n equals to m, and so we have b0, 0 of 2m is equal. So it's just, rather than working with like n over 2 and stuff like this, let's just have n equals 2m, and then we have 2m, choose m, and then p to the m, q to the m, and you can write it down like this. Okay. Now, what about summing? The other b0, 0 again. If n is odd, then b0, 0 of n is 0. Now, can we study this quantity? Can we study its summation, or basically its limit as m goes to infinity? It's a bit complicated function of m, right? So there is an m here, 2m, factorial of 2m, factorial of m squared in the denominator, and then you have p to the m, q to the m, okay? And so how can we study basically a quantity as such? So one standard way of doing this is the Sterling approximation, and basically it has a number of forms, and the form that we use here is that basically the factorial can be upper bounded and lower bounded, upper bounded by this term and lower bounded by that term. Okay. And now we start lower and upper bounding each factorial that we have in our expression. So 2m, again, use that expression with v equal to 2m. You will have an upper bound and a lower bound. Applied to m, you will have a lower bound and upper bound. Take the reciprocal 1 over the factorial of m, and then basically the upper bound will be the reciprocal of the lower bound on m factorial, and the lower bound on 1 over m factorial will be the reciprocal of the upper bound on m factorial, and then square both sides, and then multiply these two guys, and this is what you will get. You will get an upper and lower bounds on, basically, remember this quantity is 2m choose m, or 2m factorial over m factorial squared. So this quantity is upper and lower bounded by, again, factorial is like difficult to know like what is going on when you take limits, but now we have upper and lower limits, and those basically involve like 2 to the m or 2 to the 2m, and then 1 over square root m. So these things are manageable. We can take their limits. We can study, if we sum, we can study whether the sum converges or not. Okay, so the trick is to use a Sterling approximation. Okay, and here I want actually a lower and upper bound to make sure about my result, right? So if it, you will see this in a minute. Okay, so this is B00 of 2m, and this thing can be written as such, and this thing can be written as such. And before proceeding, it is like sort of nice to study this quantity, 4pq. So there is a quantity that depends on the b value, and q is 1 minus p. So we want to study it. Again, it's important. You have something raised to the power m, right? It is extremely important to know whether this thing is equal to 1, because in that case 1 to any power is 1, or is this thing greater than 1? In that case you have something that is exploding, or if this thing is strictly less than 1, in that case you have something that decays to 0. Okay, so before proceeding, it is basically very helpful if we focus on the function for p1 minus p. So p is a number between 0 and 1. This is the probability to go from state n to state n plus 1. So b is from 0 to 1, and this function is a quadratic function, and it looks like this. So it is 0 at 0, it is 0 at 1, and it reaches its peak at 1 of 1 at 1/2. So basically this j is strictly less than 1, okay, for basically b not equal to 1/2. And j is equal to 1 if b is equal to 1/2. And so basically for the simple random walk, this term here will be exactly 1, and 1 raised to the power m is 1. But if you have basically a random walk that is not simple, in which b is not equal to q, then for bq is a number that is strictly less than 1, and when you raise it to the power m, then you have something that decays exponentially, and this is important when we do limits and summations. Okay, so let's first focus on the simple random walk. So for the simple random walk, this 4pq is equal to 1, and basically what you have is 1 over square root m. 1 over square root m, and this decays and goes to 0. Okay, so basically limit n goes to infinity of b00 of n is actually 0. Remember that the b00 of odd time instance is equal to 0. Now we have shown that the probability at even time instance actually decays also to 0. So the sequence as a whole decays to 0. So this means what? So now our possibilities are either transient, either state 0 is transient, or state 0 is null recurrent. It cannot be positive recurrent, because for a positive recurrent state, this limit here should be something that is positive. So we got a 0, indicating that basically we have a state that is either transient or null recurrent. Now, if you sum, what is the summation of 1 over m to the power 1/2? 1/2 is less than 1, and so we know that this is basically a divergent sum. So this summation here is in fact infinity, and because this summation is infinity, it means that state 0 is null recurrent. So this is an example. This is the first example in which you encounter a null recurrent state. Null recurrent states can never occur in finite Markov chains. Okay, and in the homework you will basically explain why in a finite Markov chain, a Markov chain with a finite state space, basically you can never have a null recurrent state. But you can have null recurrent states in infinite discrete time Markov chains. Why is our Markov chain now infinite? Why it's infinite? Why is it infinite? Because every integer is reachable, no matter how large, right? So I explained this earlier, that basically can you reach the state a trillion to the power trillion? Can you reach that state? Yes. One way of reaching it is to start from 0 and just have a sequence of a trillion to the power trillion plus ones, right? The probability of something like this happening is extremely tiny, but it is still positive. So every integer is accessible from 0. The summation k from 1 to n, okay, so this summation k from 1 to n dk can be any integer so long as j, so long as j, so n is large enough. Remember that this summation is upper bounded by n, and it is greater than or equal to minus. So you just wait for a larger n, and you will cover any integer of your choice. So every state, I was basically explaining that every state is reachable from 0, and by state any integer value, whether positive or negative, is reachable. It's an irreducible chain, and it's an infinite because basically the state space is the set of integers. So S here is the set of integers. Despite this fact, but note that the PMF of x of n has the support minus n plus 1 up to n. So basically every x, its PMF, the possible number of values that x of n can take for a finite n is basically something, it's a finite set. However, because n can be arbitrarily large, then any integer will be in the state space. In other words, if you doubt that the state space is the set of integers, give me an example of an integer that cannot be actually be reached by this discrete time Markov chain. I mean, cannot be reached with almost surely. No. There is no integer that cannot be reached almost surely. Every integer can be reached. Okay? So the state space is actually the set of integers. It's an infinite space, a state space, and now we can have those mysterious non-recurrent states that can never ever occur in a finite Markov chain. And because the Markov chain is irreducible, then actually every state will be non-recurrent. Now, what if B is not 1/2, J is less than 1? So basically we have J here raised to the power M will be less than 1. Now the limit will be 0, but what about the summation? If you sum, you will get 1 over square root M, but now this is multiplied by a number that is less than 1 raised to the power M. So the exponential decay will dominate and the overall series will converge. So basically this summation will be finite. So if P is any value other than 1/2, then all the states are transient. Because this limit is 0. Again, if this limit is 0, we are basically either transient or non-recurrent. You need to go and check the sum. The sum is finite if P is not equal to 1/2, meaning that every state is a transient state, something that can never happen in a finite Markov chain. In finite Markov chain, we did the proof for this one that basically it cannot be the case that all states are transient at the same time if the state space is finite. But in an infinite, basically discrete time Markov chain, yes, we can have all states as transient states, and the random walk with P not equal to 1/2 is an example. So it's basically it's a very interesting discrete time Markov chain, you know, if you think about it, because like it gives you examples for things that we have never seen before. Okay, so you start seeing, you know, basically that it's not just that we have non-recurrent states. Every state in the system is non-recurrent, and every state is transient, depending on whether P is exactly 1/2 or not. Any questions? Now, can you play this game of classification by studying actually the F probabilities? We can do so. We will gain new insight, and you know, we can see things from another perspective. So let's now do things in terms of the F probabilities. Let's study the generating function Fij of Z. So Fij of Z, which is this generating function, it is the expectation of Z to the power Tij, given that x0 is equal to I. So given that you start in state I, you ask yourself, Tij is the number of steps needed to go from I into J for the first time. Okay, so this number of steps can be 1 or 2 or 3 or 4 or 5 and so on. And so basically the generating function is the expectation of Z to the power Tij, given that you start in state I. Let's focus on F00 of Z. So this is expectation of xz T00, given x0 is equal to 0. Now, what you will do is that you will, you know, basically do something like law of total probability. Perhaps you want to call it law of total expectation or whatever, which is that you will take this expectation, okay, and you will condition on, you will, what I will do is that I will condition also on x1 is equal to 1. Okay, and then I will multiply by the probability that x1 is equal to 1, given that x0 is equal to 0, plus expectation z t00, right? X of 1 can have just one of two values, plus or minus 1. This is x0 is equal to 0, x1 is equal to minus 1, and this is the probability that x1 is equal to minus 1, given x0 is equal to 0. Okay, now let's analyze basically this term. Now x of 0 is equal to 0, and x of 1 is equal to 1. X, you know, so basically this is equal to 0, and this is equal to 1. So what is T00? So now starting from 0, now you are sure that you made the transition to 1. So T00 becomes equal to 1 plus this 1 plus is the step that is needed to go from 0 to 1. And then you need the number of steps to go from 1 to 0. And for this one here, T00, once you have x of 0 is equal to 0, x of 1 is equal to -1, you have one step to go from 0 to -1. Now you aren't at -1, and you ask yourself what is the number of steps to go from -1 to 0. Okay, so this is the expression that we have here, after noting that this probability here to go from 0 to 1 happens with probability B, to go from -1 to 0 happens with probability, from 0 to 1 it happens with probability B, to go from 0 to -1 it happens with probability Q, and so F00 of Z can be written in this form here, and you can take Z outside each expectation, and you will be left with the generating function of T10 and the generating function of T-10. So this is a very important equation, that F00 of Z is equal to BZ F10 of Z plus QZ F-10 of Z. Of course, the bad thing is that, like, F00, it's not clear what this thing is, because it is expressed in terms of those guys, and we have no idea what those guys are. So let's start basically studying something else, F01 of Z. So again, so this will be the generating function basically of the time needed to start from 0 and to go into state 1 for the first time. So basically do the same thing. So have bx1 is equal to 1 or x1 is equal to -1. Have this probability here, which is p, this probability there, which is q. Now, if you condition on x of 0 is 0 and x of 1 is 1, this means that you are sure that you made a transition from 0 to 1. Now you want to T01. Again, what is T01? It's basically the time to go from 0 to 1. Well, we did make a transition from 0 to 1 in one step. This is equal now, given that x of 0 is equal to 0, and given that x of 1 is equal to 1. Now, given this T01 is equal to 1 almost surely with probability 1, given that x of 0 is 0 and that x of 1 is 1. You already entered into state 1 for the first time. Okay, and so basically this term here will just be z to the power 1. It will be z to the power 1, and our first term will be pz. Okay, what about the second term? This is q. What about this one? You go to -1. So what is T01? Now you move to -1. So you did one step, but then you are in state -1. Now to go to state 1, you need the time that it takes to go from -1 to 1. Okay, and so you can take a z outside. You can take a z outside, but then you have f of -1, 1. Okay, and so F01 of z is pz plus qz f-1, 1 of z. Okay. Note that because S is Z and we have symmetry, every state, every state is like every other state. At every state, you can increase by 1 with probability B, or decrease by 1 with probability Q. So it is reasonable to expect that F01 of Z is Fi plus 1 of Z. It really, F01, which we studied here, if you say replace 0 and 1 by 1 and 2, it shouldn't matter, right? Going from 0 to 1 is like going from 1 to 2, again, because of the very structure of this discrete time Markov chain. Again, things here, we seem stuck, stuck. We are stuck basically because, like, we try to compute an f of z, and we get it in terms of others, right? So stuck. So are we stuck now? So we started f0 of z. It's f10 in terms of f10 and f minus 10. And then we tried our luck with f01. The nice thing is that the first term is just bz without an f probability. But now we have f minus 1 and 1. So are we stuck? No. It turns out that this guy here will resolve everything for us. Okay, what is the story? So f minus 1, 1 of z. So what is this thing here? Well, it is that you go from your starting point is minus 1. So given that x of 0 is minus 1, you need to count the number of steps till you reach state 1. Now the first thing is that t minus 1 1 is t minus 1 0 plus t 0 1. Why is this the case? Because if you start at minus 1, there is no way whatsoever, given the structure of our discrete time Markov chain, to go to state 1 without visiting state 0. Right? Remember, our chain, if you draw it, it is, you have those guys like this. Okay, and so you go here, you go there. Okay, and so let's say that this is minus 1, this is basically 0, this is 1, this is 2, and so on. Now, minus 1, from minus 1, you can go to minus 2 or 0. And if you start at minus 1, your hope to reach state 1 must include going through or passing by state 0. Now, if there is a link, something like this, which we don't have here, this will not be true. So the structure of our discrete time Markov chain tells us that you want to go from minus 1 to 1? Okay. But basically, you need to pass through 0. So it is equal to the time needed to go into state 0 for the first time, and then the time needed to go from 0 to 1. So this is our first observation. So because, minus 1 to 1 must involve state 0. Okay. Now the next thing is to do conditioning as I did above, but in a different way. So basically, to go from minus 1 to 0. So going from t minus 1 to 0 is the first passage to 0 from minus 1. And I said in a previous lecture that first passage probabilities are stopping times. They are stopping times with respect to your random process here it is a discrete time Markov chain. So those are stopping times. Now, stopping time can basically be a proper or non-defective random variable, which means that it's the probability that the stopping time is less than infinity is 1, but it can take the value plus infinity. And we don't know. So here we don't really know what is going on. Forget about what you may say that basically things here, let's make use of the results of studying the B probabilities, but let's, for the sake of basically making the argument here self-contained, let's not use anything from the previous slide. So basically, we still do not know what is the classification of the states, okay? And now we don't know whether actually, the states are, perhaps they are transient, and perhaps those first passage basically probabilities, they do not, if you take the PMF or the probabilities, they do not really sum to 1, and there is a probability that basically this t minus 1 0 takes the value plus infinity. So what we will do is that we will split into two events. with this guy being finite and with this guy being plus infinity, and then we will condition that x of t minus 1, 0 is 0, which means that at time t minus 1, 0, the state is that you go to 0. Okay, and we will see why this is needed. Basically, this is a trick so that we can apply or exploit the strong Markov property